This is the second video, second revision video for MECN 2010, Introduction to Material Science and Engineering. It's basically revision for the upcoming exam, and in this video we will be going through a previous exam question, which is a question from May 2017. The question states, the following data was collected from a 21 mm diameter test specimen of a ductile high-strength aluminum alloy. L0 is equal to 50.8 millimeters. Pulled in tension at room temperature. After fracture, the total length was 56.642 millimeters. And then it says, use this information provided in the table to complete pass-through A. So here we've got a whole lot of force and length, and then stress and strain with a couple of the regions blanked out. So let's look at the question quickly. What information is given? Right. Oh, sorry. Just erase that. So, what information have we got? We've got a diameter. So it's telling us that our specimen is round, and we can calculate the area. And if we do that calculation, we find that the area is meter squared, 0.000346 meters squared. Remember, I always work in meters and newtons to get an answer in pascals, and then I divide by whatever is necessary to get to the right units. Second piece of information is the span length or the initial length, which is 50.8. It says room temperature here, which is an important piece of information. And then the final length was 56.642 millimeters, right? Okay, so that's the information we're given. So the first part of the question says we need to calculate these missing stress-strain data, stress in MPa, strain in millimeters per millimeters or unitless, and then we have to plot it on the graph paper provided. So first thing we need to do is calculate a stress for point 2. So we need a stress in MPa, and we know that stress is force over area. We calculated the area earlier, so it's 25,400 over 0.000346, and it gives me an answer in pascals of 73,333,978. Right, and I need that in MPa, so divide that by 1 to the power of 1 exponent 6. And that gives me an answer of 73.334 MPa. Right, so this is the first bit. Okay. The second question, part of the question says for point 4, calculate what the strain is. So now I need to work out delta L over L. And that's equal to 50.952 minus 50.8 over 50.8, which is equal to 50.952 divided 50.952 minus 50.8 divided by 50.8, which gives me a strain of 0.00299, right? And then using the same method, I'm going to calculate the stress and the strain here. So I calculate the stress as 463.101 MPa, and I calculate the strain as 0.0700. Okay, so that's the first part of the question. I probably would have gotten about 4 marks for that, right? 4 calculations. Now it says I need to plot it, right? So I've got my data here. My first point is, I should put that right on the origin. Let's make it a bit neater. My first point is the 0, 0, okay? Then my next point is 0.005, so I've got this point, right? Now we're doing this one, 0.005 and 36.7. So 36.7 is about there. Oh, I lost my origin. Okay, let's make it crosses. That will stay. Then my next point is 0.005 0, 1, and 73, so it's just about there. Okay, 0.002 and 146 is just about here. 0.0075, oh sorry, 0.003 and 220, which is about there. 0.075 and 295, so we're sitting about there. 0.015 and 344, we're going there. 0.04, which is 0.04, which is on our axis, and 432, 0.07, and 463, 0.1 and 437, and then 0.015, which is about here, and 360. Okay, so now I can draw this curve. I have to label my diagram. So this is strain, and this is stress in MPa. Remember, the units are important. Okay, now I'm going to draw a curve. I do apologize. We know my drawings are not the best at the best of times. But it would look something like that, right? And already I can see that my UTS is there. So this is my UTS point, right? And this is obviously my breaking strength. Okay, so you would obviously draw that a lot neater than I have, but that is basically what we're doing. Now the next part of the question is compute the modulus of elasticity or Young's modulus. So now we've got to figure out where the elastic portion is, right? It looks to me as if the elastic portion is these 3 points here. So what I would do is I'd take the third point, which is 73.3 minus the origin, which is 0. So I've taken 0.3 minus 0.1, and now I'm going to divide by the difference in strain. It's also 0, and that would give me 73.3, remember, 73.3 MPa. And that would give me an answer of 73.3 GPa. In essence, I would, in this case, accept an answer of anywhere between 72 and 75 GPa, depending on how you did the calculation. Right, so that was pretty simple. I just calculated the slope of that. It was the change in stress over the change in strain, right? I took this point as 3 and I subtracted 0.1. Okay, 2 marks. Then it says determine the 0.2% strain offset yield strength and indicate it. Right, so now this is a little bit tricky because our scale isn't really great here, right? So we need this correlates to a strain of 0.002. So let's say that's my 0.02, and I need to draw a line that is parallel to this one. Okay. All right. Okay, and I'm crossing my curve around about there. Right, I'm crossing the stress strain curve there with my line parallel to my modulus, and this is probably about 280 MPa. Okay, so I would say for this, my answer was 280 MPa, but I would have probably accepted an answer anywhere between 275 to 295 MPa, depending on how accurate you want to be, right? Obviously, you've drawn this by hand, so accuracy would be a little bit limited, but that would be where my 0.2% offset yield would be. And I need to indicate it. Part D says determine the ultimate tensile strength and the approximate load at yield point. Right? So we already said that our yield point, well, okay, let's do the ultimate tensile strength. That's easy. We know that this is the maximum strength, right? So it has to be 463.1 MPa. Right? We calculated that previously. Not difficult. The load at yield point would be 280 MPa times by my area. Remember my units, 200 MPa exponent 6 times. Recall memory. and that would give me a load of 96,980 newtons. Okay, obviously, once again, depends on what value I used for the yield here. If I'd used a range, I could have got a range in answers, and I could also write this obviously as 96.98 kilonewtons. And then the interesting question is, what is the correct ductility in percent elongation at the yield point? Okay, now that is a slightly more complicated question, because what we need to do here is we need to say, okay, we worked out our modulus. Our E was 73.3, right? We need to know that, and we need to know how much plasticity there is. So remember, we said if I take the, oh, sorry, I'm answering the wrong question. Correct ductility. Apologies. So the correct ductility will be the final length, or the delta L at final length divided by the original length, right? Now we know that the question gave us a final length of 56.642. We need to subtract 50.8 and divide by 50.8, and that gives us an answer of 0.115, but it said percent elongation, so 0.115 times 100, which is equal to 11.5% elongation. Okay, now the next part of the question asks for a Brinell hardness calculation, and it says we've got a 10 millimeter indenter and a 500 kilogram load, and we know the size of the indenter. Calculate what the Brinell hardness number is, and we know from our formula sheet that our Brinell hardness is equal to 2f over pi d minus the square root of d squared minus di squared, right? So it's equal to 2 times the force, which is in kilograms, over pi times, we use the 10 millimeter inventor, and then 10 minus the square root of 10 squared minus 2.05 squared, close brackets, and that would give us a hardness of 149.88 Brinell hardness. Okay, pretty simple, I'm just checking it. Yeah, 149.88 HP. Okay. Right, now, sorry, this was the questioning I was answering earlier where I made the mistake. It says, assume that the test is suspended when the applied load is 149,700 newtons. It says, determine the permanent elongation, right? So the trick here is the permanent elongation. So the first thing we need to do is, what is that stretch? So we need to work out our area, which if you had recorded it already, you would have it. I unfortunately cleared it from my calculator. So we've got a stress of 432.208 MPa. Right. 432. So it's this stress here, right? Okay. Now it says the permanent elongation. Now remember, when I look at this, I know that this displacement here, or this strain here, is a mixture of plastic and elastic. Right? Now I need to subtract that elastic from this value. So the question is, what is that elastic strain? And how do I calculate it? I take my modulus, 73.3 GPA, and we know that modulus is equal to stress over strain. So I want to know what the strain is. So I am going to divide my stress, 432.208, by my modulus, and that'll give me a strain. 432.208 MPa divided by 73.3 GPa, and that gives me a strain of 0.00596, right? Now 0.005. So if I take 0.04, which is my total strain, I subtract the elastic part, it gives me a strain of 0.034. Now I need to know what the elongation is, so I take that 0.034 and I times by 50.8, and it gives me a displacement of 1.73 millimeters. And now I have to add that to my original, and that gives me a length of 52.5 millimeters, right? And it's asking for the permanent elongation. Okay, so that is the elongation. That's the length of my specimen at, if I remove the load. Okay, permanent elongation. You notice it didn't ask me for the percent elongation, right? Because the percent elongation would have been that 1.73 divided by the 50.8, right? It just asked me for what is the permanent elongation, or what is the length of the specimen. And then the last bit of this is, what is the new yield strength? Well, we've taken the load off at that stress, so that will be the yield stress. Right? Okay. Okay, so the last part of the questions asks, if the same test would to be conducted at a temperature of 200 degrees, what would be the possible difference in the mechanical behavior of the aluminium, and must justify our answer. So what we know is that when we increase the temperature, our percent elongation is going to increase, and our ductility is going to increase. And we also know that our yield strength is going to go down, our UTS is going to go down, and our modulus is going to decrease. And the reason for this is that, firstly, the dislocation density is decreasing. And secondly, our grain size is changing. So it's getting slightly bigger. And that results in the material properties changing.